Well, thanks very much, Mo. It's an honor to be here. About the master thing, when I got a call in December that I'd been selected for that, they sent me a list of the 98 people that had been masters of the American College of Cardiology, and it turned out I knew 90 of them. The other 8 were dead, but I knew all the rest of them. So it's a relatively small community. Every time Mo asked me to speak, I was a little bit confused about what should I talk about this year. And I decided that I would defer that question to my patients because, sometimes questions that come from outside are the questions that are the most germane. I mean, if your 2-year-old asks you, why is the sky blue? That's an important question to try to answer. So the questions that I get every single day from my patients, one of them is, why do you measure my belly? Because anybody who comes to me, and for the last literally 100,000 patients I've seen, I measure their belly circumference. Some of the patients have fired me because of that. But I will tell you it's an important motivational thing because when they come back and their belly's smaller, they feel so proud. So we're going to talk about why do I measure bellies? And the other question that's germane to this is, how come I can't lose weight? And you heard about this already from the other speakers. I mean, I actually do not, as you heard from Dr. Kopecky, it's not willpower per se. There's got to be a reason why, once you gain weight, it's incredibly difficult to lose weight. And turns out the answer is in biology. And there have been some intriguing studies in the last 6 months that suggest that there's a reason why we can't lose weight. So I thought I would go into that. First, we'll talk about why do we measure bellies, and secondly, why is it so hard to lose weight? Is it because it's in our genes? Is there something genetic that makes us unable to remain skinny? Or is it in our genes, right? And I'm going to tell you already the punchline. It's in your genes with a J, not with a G, right? This isn't primarily a genetic problem. And you heard about that from Dr. Kopecky. It's habits and everything. But the bottom line is very straightforward. Once you put fat on, and I'll show you the evidence for this in a second, the fat cells generate signals that just keep saying, feed me, feed me. It's like that old, musical that they had where the monster keeps saying, feed me, and that's what happens. You put fat cells on. Those fat cells alter signaling, and one of the reasons GLP-1 receptor agonists work is that they actually interrupt some of that signaling. But the fat cells are self-promoting. They don't care about you. They're like the insurance companies. They don't care about you. The fat cells just care about themselves. They want to remain fat. So let's talk about that. These are my disclosures. None of these have anything to do with what we're going to talk about today. So first, why do I measure belly circumference? Well, the reason is because the BMI, and you've heard that all the time. This is a simple calculation that every one of your patients who has a height and a weight, the Epic and all of their systems put a BMI in there. The BMI is somewhat useful, but it really should be abandoned because there are better measures. And the reason that it even got into in sort of the medical lingo is because there is a connection here based in red. You can see the red lines, both for men and for women. The higher your BMI, left to right is your BMI, and the vertical axis is mortality. And you can see there is a correlation. High BMI people live shorter lives, right? And you already heard about this U-shaped curve because at the end of your life, you may be cachectic and dying, and that's why in the far left, very, very skinny people are more likely to die. But it turns out that the BMI is really more complicated than people think. First, it goes down with age. Now, some of this is because fat people don't live very long, right? So if you think about it, 700 people, how many 80-year-old 700-pounders are there? Right? There are none, right? So they get culled out of the crowd, so to speak. And the people who are more normal weight live longer. So that's one reason we see this. But the BMI also correlates with lots of other things. This is a heat map of obesity defined in this particular slide by BMI. And what you see is that there is a strong connection where Mo used to work down in Louisiana, for example. And Mo, I was there Wednesday by speaking in Ochsner, so it's totally different than in Santa Monica where I practice, right? But this also correlates with stroke and with many other things, poor education, diet you heard about from Dr. Kopecky. All these things correlate together. But here's a guy who has a high BMI, right? Our former governor. And obviously the problem is the scale can't discern whether your extra 20 pounds you're carrying is because of this or because you have central adiposity. So let's look at why people get overweight. So I just did the search earlier this year, and I did an internet search saying, what's the connection between family history and obesity? Because a lot of people tell me it's in my genes. The reason I'm fat is because my folks were fat, and that's why I'm fat, and they don't take any personal responsibility at all. So this is what an AI engine said. It said family history of obesity is a significant risk factor for obesity in children and adults, and this is because obesity has a strong genetic component. Well, I'm here to tell you that is not true, right? This is one of those problems when you do an AI search, because misinformation continues to be promulgated. The second half says, and parents and role models, parents are role models for their children's eating and activity habits. And that's where this particular thing falls, because family history is not the same as genetics. If you grow up next to the chemical plant, you're gonna have a different health outcome than somebody who lives further away. In Los Angeles, if you grew up within 1,000 feet of a freeway, you have a higher incidence of cardiovascular respiratory disease than if you live more than 1,000 feet away from the freeway. So there are local microenvironments, there are eating things you've heard about earlier. If your parents feed you poor foods, you're more likely to have issues. So there's clearly, family history incorporates not just genetics, but also your local environment. And even when I was researching for this talk, I looked up twin studies, and it turns out they're twin studies where you took identical twins who happened to be raised in different families to see, did they end up being obese raised in different families? The problem with those studies, it turns out, is when you're the social agency putting twins who you separate into different communities, you actually match up the socioeconomic strata of what the biologic parents were. So the studies are totally besmirched by the fact that if you grew up in this town, they try to put you with somebody in that town in a similar socioeconomic, so the studies are not believable. But family history and elevated weight track together, and that put me on this journey of, is that because of genes or because of something else? Height and weight track together, but what I want to, and exercise you heard about, no question, if you exercise more. Now, again, if you build muscle, the scale can't tell the difference. So people who are weightlifters have a high BMI, but not because they have belly fat. So family history is not genetics because family history incorporates eating, exercise, and the microenvironment. Genetics does not affect, as best we know, eating or exercise per se. And it turns out genetics is not directly dependent on the environment. You know, your genes don't dictate your local environment, but the opposite is actually not true. Your environment does dictate not your gene code, but your gene expression. And this is called epigenetics, right? So there's an explosion of epigenetic data now that suggests that your local microenvironment doesn't change your genetic code, but what it does change is the expression of the genetic code, and particularly the messenger RNAs that dictate proteins, and all these little things. For example, when you had breakfast this morning or the break, turns out you eat, you turn on about 3,000 genes, and you turn off about 3,000 genes. And that happens every time you eat. In fact, I was commenting at dinner last night, I read an article this week where every time you chew, one chew turns on a neuron in your brainstem every time you chew. So there are all these traffics that are going on, and those things actually change how the genes are expressed. The local cellular environment will alter genetic expression. And that's actually why it's so hard to lose fat. Because once you get fat, the local cells change their genetic program. And the question is, GLP-1 receptor agonists help, but in the last 6 months, it turns out that there are molecular switches that have been discovered that if you could flip them, you might be able to change this local cellular environment affecting genetics expression. Not the gene code, but genetic expression. Now, is there a genetic component somewhat? There are huge databases that have tried to do this, and the biggest ones are like in the UK where they have the biobank, 600,000 people, and you follow them over their lifetime, and there's a rough correlation in a whole genome analysis. So if I genotype every one of us here, there's a rough correlation between your entire 23,000 genes or so and your likelihood. So there is a little bit of the genetic code affects weight, but it's way swamped by local environment. So let's talk about why that's the case. First, I want to focus on the different types of adipose tissue, because it turns out that different types of adipose tissue that have a lot of different biologic actions. So maybe some women don't like the fact that they have more hip weight and thigh weight, but it turns out that's kind of inert weight. That's a storage depot. It's where fat is put aside for future use as a caloric source. But it turns out there are other fat cells that aren't just inert, they're biologically active, and these are the ones that are in the core of the body. The belly, around the heart, for example, pericardium, around the blood vessels. This visceral fat stores are totally different, and they're the ones that alter the rest of the body. They raise sugar, they raise blood pressure. You heard about inflammation, they're pro-inflammatory. We'll talk about that in a minute. You heard earlier, when you put somebody on a GLP-1 receptor agonist, turns out their need for joint replacement goes down by 50%. People thought, well, that's because they're carrying around less weight. No, it's because the joint is inflamed. And when you lower the weight, it's less inflamed. And they don't have the pain and they don't need joint replacement. So let's look at these different fat stores. So first there's what is termed healthy fat, and there are actually forms of healthy fat. And these are the types of the fat stores, as I said, that are repositories for calories and fats. And it's not noxious to have that, right? Unlike the fat on the right, which is what is termed in this slide dysfunctional fat, in which hormones are released by the fat cells, and these hormones affect the rest of the body. And some of those hormones are pro-inflammatory, some of them alter your perception of fullness and your need to eat more foods. That's why I was saying fat begets fat, because it's this type of fat that's pro-inflammatory, pro-eating more. And those are the types of fat cells that in fact promulgate themselves and why it's so hard to lose weight. Dysfunctional, as I've mentioned here, if you look on the lower part, the vasculature is abnormal, the muscle is abnormal, and this includes your heart muscle. So obese people, for example, have more adiposity within the heart muscle. You heard earlier, yes, muscle mass goes down. If you do MRIs serially on hearts, for example, the heart mass goes down, but in part that's because fat deposits within the heart are eliminated if you end up losing weight. And you also heard that you're carrying less weight, so you'll have less skeletal muscle going up. But there are all sorts of other things. You're going to hear about peripheral arterial disease later today. Myocardial infarctions, all these things are related in part to these pro-inflammatory and noxious fat cells. Now, if not all fat cells are bad, let's look at what we might be able to do biologically to alter bad fat cells into better fat cells. One good type of fat cell is called brown fat. Brown fat is the body's furnace, and what it does is it acts as the way to raise the body temperature. So if you burn fat, like burning it in a fireplace or a furnace, you generate heat, and that's what brown fat does. White fat, as I already mentioned, is the fat that's around your belly and around your hips and things, and initially a fuel source. It doesn't get burned for heat generation per se, but it is, in certain areas of the body, pro-inflammatory, pro-insulin resistant, metabolic disease, diabetes mellitus, and all the other things you hear about. Now, it turns out there are ways to measure. I was talking to Matt Budoff, of course, whom you heard earlier today, and the CT scan, one of the advantages of the CT now is they can actually measure how much fat is around your heart and around your pericardium, because it turns out that is a local environment where noxious things are eluted by that fat into the coronary artery bed and actually worsen coronary disease. So there may be more than just looking at the artery, that maybe that the CT scan will also give us insight into people who are having these noxious local environments altering coronary disease. But we're going to focus on visceral or belly fat. And that's where the action is. So why do I measure belly circumference? It's because belly circumference tells you a heck of a lot more than the scale does about somebody's likelihood of developing a cardiac event. So left to right is BMI, and below 25 is considered normal. 27 to 30 is overweight, above 30 is obese. And you can see if you go left to right, yes, there is a connection. Those white bars, 1, 1.4, 1.8, those are an increased incidence of cardiac disease related to BMI. But if you look at from the front to the back, that's just measuring a very simple binary measurement. These are Caucasian women. This particular number doesn't hold for Asians, but if you look at Caucasian women and just stratify all the women who have abdominal circumferences greater than 35 inches versus those less than 35 inches, look at the difference. If you're greater than 35 inches in the dark bars, you're way more likely to have a cardiac event regardless of your BMI. And that's because there's some people who, according to the scale, their weights aren't that bad, but they have rotund bellies because of abdominal visceral fat. And you can see that the predictiveness is more than twice as high. It's about 3 times as high, just pulling out a tape measure and measuring the belly instead of using the scale as our discriminator. And indeed, if you look whether it was smokers, non-smokers, this particular men on the left, women on the right, and you look at waist circumference left to right, and this is a very steep graded thing, that the thinner you are around your belly, the better off you do. It's not binary, yes or no, 30 and 33. You heard earlier, and I would agree with Dr. O'Keefe, you want your abdominal circumference to be less than your height, 50% less than your height, and that indeed, there's a strong connection between normal belly circumference and height. It's driven mostly by height. These particular numbers are just looking as a unimarker, your belly circumference. But here's a very interesting way to display it. Left to right is BMI. The vertical axis is the hazard ratio of death. And what we're looking at for each of the weight BMIs is, for example, let's take the second, let's take this one right there, okay? These people have normal BMIs. They're 20 to 22. Most of us would be proud to have a BMI of 20 to 22, okay? But if you actually look at the vertical axis, going left to right is what your belly circumference is. And for every single BMI, if you have more abdominal circumference, your risk of a heart attack or dying early is dramatically higher. In fact, you can be normal weight, even underweight, you can be overweight, you can be obese, and in every single category, that black line is going up steeply depending on your belly circumference. So we really shouldn't be measuring BMI per se. Just pull out a tape measure. It takes less than a minute to measure the abdominal circumference. And as I said, I've done it in every patient. I know Dr. O'Keefe does as well. That's the way to determine what somebody's individual risk is. And here, the green line is the line of unity. All the black lines are the prognostic value of waist circumference, independent of everything else. Are you a smoker or not? Do you have hypertension? Are you diabetic? Are you not diabetic? It doesn't make any difference, right? Belly circumference is the marker. And that's because abdominal fat is noxious. So belly fat is the enemy, right? So why is it so difficult to get rid of that? I already told you a little bit. It's because belly fat changes the environment of your body to try to promote its own existence, right? So let's look at that. It is in your genes, sort of, but it's not really in your genes. It's in the gene expression. And it turns out that once you have belly fat, it changes the gene expression. It's a local phenomenon that is an epigenetic that changes the fat cells to exude different substances that promote their own well-being. And these are called molecular scars. So epigenetic tells us that once you've gained weight, even if you lose the weight, there's a memory of the cells that used to be fat. And that memory persists and tells the body, even when you go off, why somebody asks, how come when you go off the GLP-1 receptor agonist that 75 to 80% of the people regain weight? It's because the remnants of those fat cells still have molecular memory of when they were fat. And that's the RNA of the fat cells. It's not the DNA. The code hasn't changed, but the expression has changed. And I'll show you the evidence for that now. So what is epigenetics? It's when you have changes that don't change the source code. The blueprint is the same. Your DNA isn't changing. What does change is the expression of those. Right? And that's due to environmental factors. These include various things, biologically, histones and other RNAs and methylation and various things like that. But that's what happens to the fat cells. So let's look at the evidence for this. Here's an interesting study where they did bariatric surgery. You heard earlier that maybe the GLP-1 receptor agonist will obviate the need to do bariatric surgery. Well, it turns out that bariatric surgery actually is a little more effective long-term than even GLP-1 receptor agonists. But this is a very interesting study where they had people, small study, but nonetheless they all underwent Roux-en-Y, usually, or gastric sleeve. Those are the only two really that are still being done and that work. And they're followed for a couple years. And all of them had dramatic weight loss, more than 25% of their body weight. And then what you ask the question is, if you take their fat cells, when they were fat versus when they are now normal weight, how do those fat cells look compared to normal people? And won't belabor the point, but a lot of these people lost a tremendous amount of weight because bariatric surgery works. This is the complex slide, but what I'll just tell you is 2 years later, after the person has lost all their weight, you wait 2 years and then you biopsy their fat cells. It turns out their fat cells never returned to normal. The fat cells have shrunk, but the gene expression in those fat cells remains abnormal. Some genes are turned on, some are turned off. The RNA is different, but that doesn't go away with weight loss, which is why when you go off a GLP-1 receptor agonist, the weight usually comes back. This has been now replicated in animals. There are some beautiful mice and rats, and how applicable are mice and rat studies to humans? We're not sure, but it's been shown. In green here, you see what happens when the mice are, and this particular study did an interesting study. They basically force-fed the mice to make them fat, and then they put them on a diet. Okay, so this isn't obese genetic mice, which they do have. These are normal mice who are overfed, and then they allow them to go back to weight, and you can see that's what happens at the end here. And this is a relatively short-term trial. This is 8 weeks of going on a diet and losing weight. And again, what these maps show is what happens to the RNA of animals that used to be fat that lost weight, and it turned out they look just like the fat animals. That losing weight with diet, or in the previous study, with surgery, didn't change the molecular expression in the fat cells. That's what those things mean. And it wasn't just fat cells. They looked at white blood cells. This is because, remember, there's a correlation between fat and inflammation, and it turned out macrophages in these same animals, having nothing to do with their fat, adipose, but they had also been reprogrammed and didn't deprogram, even going on a diet. So adipose tissue alters genetic expression, even after weight loss is achieved, whether that's with diet or with Roux-en-Y or gastric sleeve surgery, and those changes persist for at least the next 2 years. That's why it's so hard to lose weight, and it's not limited to fat cells. Turns out that when they looked at endothelial cells within blood vessels, those were altered, so were the inflammatory cells like macrophages. So these are persistent changes that once you've had the fat, now you have a memory that's there. And that explains why people can't lose weight. Feed me, feed me. And indeed, when you allow the animals to refeed, the ones that used to be fat, even if you now force feed them, they gain fat at a much greater rate. Their weight goes up way faster because the fat cells are very effective at storing fat. So let's explore that a little further, because there was an intriguing study in the last 6 months that suggested there may be a solution to this. And that's to harness the body's own ability to burn fat in brown fat cells. What is brown fat? Here's an infant, and it turns out babies don't shiver, right? To generate heat, if you get hypothermic hiking up Shasta, you're gonna shiver to try to generate heat. The muscle cells will generate heat, but babies don't have that ability. So the way they generate body heat is by burning calories in brown fat, which is in the core of the body as depicted here, the sternum and other parts of the body. And usually as we get older, the brown fat dissipates. So there hasn't been a lot of action looking at brown fat in adults. It's a big deal in babies. But it turns out that brown fat is one of the reasons why there are differences in all of us in terms of ability to lose weight or gain weight. Brown fat cells have beta receptors on them, the same beta receptors that are in your lungs and your heart and elsewhere. If you look at the literature carefully, when you put people on a beta blocker, whether it's for hypertension, heart failure, the average weight gain is about 2 kilos on a beta blocker versus no beta blocker. Why is that? It's not because they're doing less activity. That's been looked at. Turns out it's because they're brown fat cells, and when you block the beta receptor in the brown fat, you turn off some of the burning of calories in the residual brown fat in adults. So there's a connection between the beta receptor, beta blockers, weight, here depicted by brown fat. And that was the aha moment, because when you go downstream in a brown fat cell and say, okay, when you stimulate the adrenergic beta-1 receptor, downstream, how does the cell know to start burning fat? And the answer is down in the lower left. It turns out there are molecular markers inside a brown fat cell that you can selectively turn on or genetically manipulate. Now think about that. You have brown fat still in your body. If you could flip a switch and have those brown fat cells start burning fat, you can burn calories while you're just standing there doing nothing, you know? And if you burn calories, what's gonna happen? You're gonna lose weight. So once they found this, they said, let's see if we can actually do that. They did it by using I started life as a cell biologist, so this is really interesting to me. But the reason that it's interesting to all of us is because this is maybe the next way to have people lose weight. This is what I call the Gretzky approach, right? Wayne Gretzky, the hockey player. Don't act where the puck is now. Where's the puck going to be? That's where you want to be. This is where we may want to be in a couple years. Because if you could harness brown fat and turn on burning of calories, you'll have people lose weight regardless of what else they do. And let's see if that actually can happen. Well, some people, this happens to be from Gladstone Institute down in San Francisco, down a ways here, turns out that you can, in fact, harness this. And the way they decided to do it was to take fat cells, your own white fat cells, and there's enough plasticity biologically that you can take a white cell and make it become a brown fat cell. Usually your brown fat cells sort of dissipate, but you have plenty of white cells. How about if you take those white fat, flip some molecular switches, make them become brown fat cells, and then make those brown fat cells burn weight? Wouldn't that be a good thing to do? Well, can you do that? The answer is yes, you can do it. You can look up this article. I won't go through this. Oh, let me go. Yeah. What happens is when you do that, you burn fat, the animals lose weight, and their temperature goes up. Now, you may remember there were people who always would come to your office and say, can't you put me on thyroid hormone so I'll just burn more calories? Doesn't work. This actually works. It works at least in animals. And it works in human cells. They haven't tried to get in people, but they can show in human cells that in the Petri dish, you can convert white fat to brown fat, burn calories. And as I will show you, that happens to lose weight in animals. So here is an animal that's bred to be obese. Hopefully you don't have these types of animals running around your house. These are obese mice. And it turned out when you manipulated the mice in the way I just mentioned, they lost 35% of their body weight right out of the gate. They just went down, 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 like being put on a GLP-1 receptor agonist. But all these mice had done was to convert white fat to brown fat. And they did that by doing these receptors in the fat cells, altering the biology of the fat cell. And what I'll show, we don't have to go through this, but on the left is a heat map. This is an infrared camera looking at the mice. And the reason they lost weight is depicted in red in the lower left, that's the heat map, is because these mice are burning 24/7, they're burning calories because they've converted white fat to brown fat, okay? And if you actually look at, let me see if I have this here. Yeah, their body temperature went up 1 degree. Now, you may not think 1 degree, but think about it. If your normal temperature is 97.5 or something, and it's 98.5, most of the calories you burn per day are not walking. Most of the calories you burn per day are to generate heat. And 1 degree 24/7, you will lose about 1/3 of your body weight, just elevating your temperature internally. And they did that because they converted the bad white cells to good brown, or maybe you can call them beige. That if you read the literature, that's what you'll see. And it leads to weight loss, and importantly, it's not just the weight loss. If you do inflammatory markers, people asked earlier about CRP. If you measure CRP and those kinds of things, does it go down? Yes, it goes down in these animals as well. So all fat is not bad. White fat is the problem. It promotes inflammation, insulin resistance, higher blood pressure. The fat feeds itself by changing genetic expression. The solution in one way would be never to get fat in the first place, right? Because if you don't get fat, the fat cells won't be saying, feed me, feed me. But unfortunately, partly because, as Dr. Kopecky said, we're exposed to unnatural things that we didn't evolve with. Most of us have the propensity, the ability to get fat. And once that happens, it's really hard to recoup this. But maybe one of the answers, these emerging answers, will be to convert the bad fat to good fat and reset the whole system. And I thank you very much for your attention today. Questions?
Yes?
So if raising the body weight or raising the body temperature can help people lose weight, should we be telling our menopausal women to not get rid of their hot flashes?
The question, if raising the body temperature can cause you to lose weight, should we tell our menopausal women not to worry about their hot flashes?
I have no idea whether, I mean, maybe Dr. Kopecki or somebody would know. Are hot flashes associated with good or bad outcomes? I actually don't know the answer to that. I mean, obviously, symptomatically, there are medicines people get put on or estrogens, but is that a good or a bad thing to do? I don't have any clue. It's a good concept, though. I mean, I'm often asked, well, what if we just wear those hot suits? You know, you walk around in suits all day. The problem is it's hard to generate heat 24/7 by walking around in a thermal suit or getting in a jacuzzi. But it may be that raising body temperature is not a bad thing. At least in these animals, it works quite well. There's a question. Yeah.
People are talking about doing cold plunging because warming back up burns more calories than this or that. True?
Warming, yeah.
People are talking about cold plunging and whether warming your body
Yeah.
temperature back up causes some weight loss.
So there is a little truth in that, in the sense that, think about it, if you drink a beverage that's 98 degrees, you know, your body doesn't have to do anything with it. If you drink a beverage that's 40 degrees or 33 degrees, like a refrigerator temperature, you have to bring that up to a certain temperature. And as when you're cooking or heating up water, it takes a tremendous number of calories to heat from cold to hot. So there may be some merit. Now, whether sitting in a cold plunge, as you say, or you know, in an ice-filled lake around here is a good idea. There are lots of, you know, why is the diving reflex? You go into cold water, your heart rate goes down, there's vagal, and it's more complicated than that, but do I think that's a bad idea? I actually don't think it's a bad idea. I'm not aware that data suggests that it's useful, but it would be, I think, worth looking at, for sure.
Yes.
You mentioned changing fats and how that decreases inflammatory markers, but does it translate into less cardiovascular disease?
So the question is, if we alter fat and get less inflammation markers, does that actually translate into clinical benefit? We think the answer is yes, and we know for sure from GLP-1 receptor data that you heard about earlier that once you put somebody on such a drug, the traditional markers we use of inflammation, whether it's CRP or interleukin-6 or others, do improve. And actually those improve with exercise and weight loss and other things. Is that one of the reasons that it benefits? We're not sure. But there's certainly a line of evidence. The colchicine became a little mixed because there are 3 colchicine trials. 2 were positive, 1 was neutral in terms of benefit. Canakinumab, an interleukin-6 antagonist, helps prevent heart attacks, and that's just a pure anti-inflammatory. So I do think that reducing inflammation has cardiovascular benefit, whether achieved directly with medicines or indirectly with exercise, weight loss, et cetera. So do I think it's a good thing? Yes, I do. Now, and I think Matt Budoff had mentioned that even aspirin can reduce CRP. I don't know about 81 milligrams, whether it reduces inflammation, but certainly non-steroidals do a little bit. But I will tell you, there are also anti-inflammatories that didn't pan out. You may know there was a methotrexate study done that showed no benefit in terms of preventing cardiovascular. So it may depend where in the inflammasome that we actually target to help prevent cardiac events.
Yep.
Likely a cruder model for this idea about white fat cells. Has there been studies looking at liposuction, removal
Yeah.
of white fat cells, and how that affects decline?
Yeah, so the question in here was, is there a role for liposuction? I actually get that question quite a bit. And as far as I know, nobody's liposuctioning the fat around your heart, for example. Or at least if they offer you that, I would deny it. I would tell them that's not a good idea. Turn that away. But one of the problems with liposuction is if you remove the fat cells from your hips and your thighs and other places we're wanting, look, I'm in Hollywood, people want body sculpting, and those are fat cells that don't have any noxiousness. The belly fat cells, it's pretty hard to do liposuction of the fat that's around your visceral gut, right? I would say that's not going to happen. You know, I mean, the pannus and the omentum and things. So the subcutaneous fat isn't where the action is. It's the perivisceral fat where it's dangerous to try to suck that out of the body. That's why liposuction hasn't worked.
Yes.
Yeah.
Regular exercise increase your basal temperature?
Does exercise increase your body temperature? It certainly does when you are exercising. I am not aware of data that say that after you've completed exercise, that the body temperature is higher than it would have otherwise been. I'm not aware of any data about that.
Anything that might decrease that fat memory cell? Any activity, any aspirin, any particular?
Yeah, so the question is what other approaches, if any? Once you've already gained the weight, are you stuck? I mean, those last few experiments that I showed you that were done in mice and in human cells, et cetera, tried to answer the question by actually going into the fat cell. And, in the past, we've looked at all these other fats. We haven't really tried to change the biology of the fat cell. But for sure, in these animals and in tissue culture, if you alter the fat cell, then you do, in fact, get rid of the memory that you mentioned. How do we do that practically right now? I'm not aware of any way to do that. And that's why, if you lose weight, why does Jenny Craig nut permanently lower your weight? The same reason the GLP-1 in most cases doesn't permanently lower your weight. This is why, because there's this memory. So do I think there will be a solution? I can guarantee you that pharma's all over these types of things, because already the GLP-1s are a $50 billion business. Imagine here if you could convert your normal cells and lose 35% of your body weight with a pill that just alters the white cells. I mean, that would be huge, because it doesn't have any GI side effect, et cetera, et cetera. So might that pan out? Maybe, but this is in its infancy. Most of the data I showed you were in the last 6 months. So these are in the basic science literature. They haven't yet come into the clinical literature yet.
We have a question over here first.
So water fasting has been shown to induce apoptosis of cells that are not being productive in the body. And I was wondering, you probably just answered my question, if water fasting can induce apoptosis of the fat cells.
Yeah, you heard, so the question is about fasting, and you heard earlier about intermittent fasting. And it is true that the SGLT2 inhibitors mimic, in certain ways, the fasting state. And one of the slides I showed you that had the word ferroptosis and stuff. So there are ways that the body culls out cells that are either not doing their job or whatever. That's one of the ways. And indeed, intermittent fasting appears to accomplish that. The problem is it's pretty hard for most people So I did a stint when I was back at the Brigham, we had a clinical research center where we had a total fasting. We were actually doing military research on complete fasting. We had people in a locked ward where we didn't feed them for a year. They got fluid, they got minerals and vitamins, they got no food for 12 months. And these people, the average weight when they came in was like 700 pounds. They would lose about 350 pounds. Okay, all of them. And some of them needed panectomies and all that stuff. The problem was, as soon as they got out of the locked ward, they ran across the street to the burger place and they would eat 10,000 calories. I mean, it was unbelievable to me to see this, but it's because of this molecular memory. Now, if they did intermittent fasting, might that nip it in the bud? Maybe. I think it's a legitimate thing to try. The problem with intermittent fasting, it can't be, I mean, think about it. All of us here intermittently fast. We don't eat while we're asleep. The problem is that 8 hours is not enough time to do the molecular switches. You really have to have like over 16, preferably something like 18 hours of fasting before the switches flip and say, okay, let's start producing ketones and let's start using fat cells and stuff. So if you said to somebody you want to put them on an intermittent fast where they only eat 4 hours a day, that actually can work if people stick to it. Problem is it's pretty hard when we nosh and have all these things, right? But it could work, yeah.
Yes?
So these these yucky white fat cells, I saw you had 2 years. How far are we studying? Like, will they change?
And so the question is, how long is that memory? I don't know, because these studies are brand new. So they didn't do these studies 10 years ago, right? So I don't know how long they'll last. But when the molecular changes that occur in RNA at 6 months, at 12 months, and at 2 years are identical, right? Now, might that change, as you're alluding to, at 4 years? Maybe. I don't know. I kind of doubt it, honestly, because 2 years is a pretty long time when things are changing minute to minute in your RNA production. So 2 years to me would be long enough to say, maybe it's permanent, but we don't have those data.
Yes?
What's the latest on colchicine?
What's the latest on colchicine? So there have been 3 randomized trials using colchicine in patients at risk for coronary events, right? Either at risk or having had a heart attack and then put on colchicine. The first 2 trials were positive, meaning there was a beneficial effect of colchicine in averting subsequent cardiovascular events. The 3rd trial, which came out most recently, was neutral. It didn't show that there was any benefit. Now, some of it was besmirched by the fact it was done during COVID time, and the FOBs were different, and the patients were different. So I think that it's hard to ignore 2 positive trials. Now, a 3rd trial negative. So the general feeling is that colchicine probably isn't needed in everybody, but you heard a little smattering of that earlier. Maybe people that exhibit, as the question was a moment ago, an elevated CRP, maybe that would be somebody we would selectively put on colchicine because they have active inflammation going on. We also still use it in people who have disease that isn't responding as well as you'd like. I mean, I had a guy who came to me, he just had his 27th stent, okay? Now, if you've had 27 coronary stents, there's something wrong with you, you know? So in those people, I pull out all the stops because, come on, you know, this person is expressing themselves as a biologic weirdo, you know? And so, yeah, we do more there.
Question in the back.
Yeah, so the question is, where do you measure belly? So my standard is I measure it when somebody's lying down. And the reason is because when they stand up, you know how really fast, it's like it droops down to their knees, and you go, where the heck do I even measure this? So it's when they're lying on their back, and I measure it wherever the maximal circumference is. For most people, that's above the umbilicus, actually, right? And I just tell them, because the standard answer, and if you do this, I get the same answer every day. That can't be right. You measured 40 inches, and I wear a 36-inch pant. And I say, yeah, you're like the gangbangers. You're wearing it way down here, and the belly is above your belt, right? That's where people hang over. So I measure it at the maximal abdominal circumference, which is usually a few centimeters above the umbilicus, usually at the lowest costal margin on the sides. That's typically where the typical person is. One of the problems is as people get older and their vertebrae shrink, the ribs get closer and closer to the hips, and it becomes more difficult. And I will just tell you, having literally measured 100,000 bellies, that it's not that easy, and some people go, where the heck do I even measure these people? But there will be people on the scale who will look grossly obese, but they have hips that are way out to here. And then when you measure their abdominal circumference at their umbilicus or above, it's perfectly fine, right? So those are good people because you've de-risked them, if you will. Great. Well, thanks.
If there's
I'll be
no more
around for any additional
Questions then.